Okay, hello. I've been looking over this whole condition with testing, and everybody's saying, "Wow, we should be testing more." But there's some issues with testing that we have to take into account, and it's really important that we do so. Otherwise, we don't. Testing may be futile, or at worst, it doesn't really achieve what we want it to achieve. For a test to be valid, it has to be able to test what it was designed to test. Two measures of validity in testing are sensitivity and specificity when it comes to screening. So here we're screening for this virus, SARS-coronavirus 2. It's what it's called. And so we want to make sure we have sensitivity and specificity. So sensitivity is defined as the probability of testing positive given one is disease positive. Specificity is defined as the probability of testing negative given one is disease negative. So here I have this nice little cross tabulation that basically tables whether or not one has the disease or does not have the disease, and whether or not one tests positive or does not test positive. Having the disease is what we call population prevalence, so that's the number of existing cases at any time out of the whole population. Does not have the disease is obviously 1 minus prevalence, so that's just the complement of that condition, because there's only two possibilities, either having the disease or not having the disease. And so there are four different options here, possibilities here, excuse me. If you have the disease and you test positive, that's a true positive. If you have the disease but test negative, you're a false negative. If you do not have the disease and test positive, you're a false positive. If you do not have the disease and test negative, you're a true negative. So this box is sensitivity, and this box here is specificity. Testing negative for the disease given your disease negative. All right, so let's apply this to this SARS-coronavirus 2. So this is the best article I've been able to find so far on sensitivity and specificity. This is the source if you're interested. It's by this author, Development of Clinical Application of a Rapid IgG combined antibody test for SARS-coronavirus 2 infection diagnosis. So I created this little cross tabulation, but I left everything blank here. So we have either people being disease positive or disease negative. So I took the current prevalence of coronavirus. At least this is this morning. Today's the 19th, and there were 9159 cases out of our ginormous population of 329, 376, 739. So if our sensitivity is 0.8866, so that's the probability of testing positive given one is disease positive, let's actually go ahead and calculate that. So I'll get on my calculator, so we have here 0.8866 times 9159, and that equals this number here, 8120. So this is 8120. So 8120. Okay, so testing negative would be the complement of that. So that would be, the remainder would be 9159 minus 8120. If you're one of my students, you're probably used to this kind of stuff. I make you fill out these tables all the time. 1039, 1039, so it's 1039. All right, there you go. Look at what this says. This says that of the 9159 true disease positives, 1,039 will test negative. So this sensitivity issue is very, very important. And I know right now we're just in this frenzy to get testing done, but unless we attend to sensitivity and specificity, we're going to get a lot of negatives, false negatives. And that's not good, because those people will go around spreading the disease to others. Let's go ahead and do specificity. So here we will be multiplying. So let's clear this bad boy out. So we've got 0.9 0.063 times this ginormous population number here, 329,367,580, and we get, wow, that's a big number, 838. All right, so there you go. So in order for, this is, here is the false positives, because these people do not have the disease, but they end up testing positive. 386174, and then then we can just add these together. 3869, 3869, 862, and then this. Completed our table, but if you'll notice this, there will be a lot of false positives here. Wow, that's a lot of false positives, right? That's like over 31 million false positives. This is part of testing. So these tests are not perfect. So just I want you to keep that in mind, since we're worrying a lot about tests. Let's also calculate what's called the positive predictive value of a test. So normally, in a disease of this magnitude wouldn't concern us because the prevalence is so small. So in reality, we wouldn't even screen for it. Screening in public health is only done when we have a real need to screen, when there's like a high prevalence condition. So let's go back, let's enter some of these values here. So this is called Bayes' formula, or Bayes' equation, or Bayes' theorem, whatever you want to call it. And I'm not going to go into all this, but what we have here is we have some kind of a conditional probability here, and the denominator is the total probability of testing positive, because you can test positive when you're disease positive, but you can also test positive when you're disease negative. So this is called the total probability. So in the numerator, you actually have the sensitivity and you have the prevalence. So you see sensitivity and prevalence, and then here you'll have again sensitivity and prevalence, because those are part of the testing positive. And then you have a false positive rate and 1 minus the prevalence. So you'll see that in the denominator. So let's go ahead and do some of these calculations here. Let's do this calculation. So our sensitivity, we know, is 0.8866, and our prevalence, what's our population prevalence? So this is actually our prevalence. As you can see, it's very, very small. Again, our population is large, so this is the probability of having the disease at this moment being an active case. So it's very, very small. Now, in the denominator, you can also, total probability of testing positive include those who test positive given they have the disease. So that's basically our measure of sensitivity. That's why we have sensitivity here, times the prevalence, and then I'm not going to go into why that is, but that's part of a multiplication rule in probability theory. And then we also have the false positive, because see, out of testing positive, you can be a true positive or a false positive. So a false positive is just 1 minus, it's the complement. It's a complement of a true negative, right? So you can, under a negative disease status, you can either be a true negative or you can be a false positive. Those two are complements. And in probability theory, complements all possible events in a sample, probability of all possible mutually exclusive events in a sample size, in a sample space, have to equal 1. So the complement of specificity is 1 minus specificity. So if I just do that here, let's see, I clear that out. So it's 1 minus 0.9063, which I have up here, right? 9063. That equals 0.0937. So this would be 0.0937. 0.0937. Then finally, we have 1 minus prevalence. Okay, and the last thing is 1 minus prevalence. So I took this large, giant, or this very, very small number, subtracted it from 1, and I get this horribly large probability 0.9999. Wait, what was it again? There's a lot of nines there, right? You know, I'll include all these digits for accuracy. 72192936619. All right, there you go. So now we have our equation and we're good to go. So we just need to complete this and we're done. And so I actually did that already. I do this every day for you all. This tells us that the probability of being disease positive given you test positive is 0.0262%. Yikes, that sucks. For that reason, we wouldn't normally screen for coronavirus disease, coronavirus too. We wouldn't be screening for that because this is a waste of public health funds in a normal situation. But because this is an emergency, yes, we are screening for it. But if we weigh this compared to a disease like type 2 diabetes or something like that, where it's much more prevalent and much more serious, we would never spend public health dollars on this. But I just wanted to give you this update on, or this lesson on how we calculate sensitivity and specificity and positive predictive value, because you'll see these numbers or these tests floated around a lot in the next few days, and people are saying, why shouldn't we test more? We should be testing more. Well, we can't just test when our tests stink. They're not doing what they're supposed to be doing. So we have to take time to develop the tests, and that's what we're trying to do. You got to have faith in science. Stop asking everybody to rush so much. But, you know, that's human nature. So thank you.